Hello, my name is Yansh Kumar, and this is Project Granite, episode 5.5. I was trying to make an episode 6, but I had to get into context, and things got really complicated really fast. So let's go through this quickly. What is stellar metallicity? Stellar metallicity is the proportion of a star's mass that is not hydrogen or helium, which is important because most stars only ever fuse hydrogen until late in their life, and because only hydrogen and helium existed in the early universe, as well as a tiny bit of lithium. The Sun, for example, has 1.2% metallicity, but mu Arae has about 2.4. The graph to the side displays the universe's baryonic normal mass composition in terms of the elements. So this table shows the 10 most common elements in the universe's mass percent. Well, the table's technically below now, but as seen with the above graph, which does talk about number of molecules, but the overall trend is kind of the same, with the exception of lithium, beryllium, and boron, which are very rare. Abundance shows a fairly consistent decrease, with even atomic numbers being more abundant than odd atomic numbers. And hydrogen and helium were principally formed through Big Bang fusion. Lithium, carbon, nitrogen, as well as some lower elements in periods 5 and 6 being formed through dying low-mass stars, like red giants. Most of the period 3 elements, as well as oxygen, fluorine, neon, and some of the period 4 elements being formed through supernovae. The other period 4 elements formed through exploding white dwarfs, as well as some silicon, sulfur, and argon, and beryllium and boron made through cosmic ray fission, as well as some of period 5, period 6, and practically all of period 7 being made by merging neutron stars. Metallicity can also be measured in dex, the log 10 of the metallicity relative to the Sun. Here are some examples. Metallicity is inversely proportional to age, and metallicity in dex can be approximated by the following equation, where x is the time since the beginning of the universe in billions of years for the inner thin disk. However, and only for the inner thin disk. However, it can vary by plus minus 0.4 dex even in the same region, and can depend on other factors outlined later. As of now, we've been assuming that dex values accounted for the entirety of metals. However, dex really only accounts for the relative abundance of iron. So technically, higher dex values have less metals than shown, and vice versa for low ones. For high dex values, relatively low mass stars that burn slowly are more abundant, like carbon and nitrogen, and many transition metals. While for lower dex values, very heavy stars would be able to fuse alpha particles into carbon, making oxygen, neon, magnesium, silicon, and sulfur more abundant. I mean, still less abundant overall, but still more abundant relative to, carbon, for example. Stellar metallicity is also determined by location within a galaxy, or even the galaxy type, as shown by the diagram to the side. So for example, in the inner thin disk, it could be 0.2 to negative 0.4 dex for new stars, and negative 0.1 to negative 0.5 dex overall. For the galactic center, it's negative 0.2 dex overall. While it would theoretically be 0.2 dex for new stars rarely ever come in there. For the thick disk, it's negative 1 to negative 0.3. For the inner halo, it's negative 1 to negative 2.2. And for the outer halo, it varies widely from negative 0.8 to even negative 3.5. Elliptical galaxies typically have much more uniform metallicity gradients, and it's also higher, typically ranging from 0.2 dex near the center to negative 0.8 dex at the outskirts. Their magnesium to iron ratio is also twice as high for some reason. And smaller galaxies usually have lower metallicities than larger galaxies, and as I said before, neutron star mergers and quasars can enrich an area. So there are three galactic populations. Population 1 in the thin and thick disk is less than 9 billion years old and have regular orbits. Population 2 is 10 to 13 billion years old and has erratic orbits. And Population 3 is a hypothetical population of stars which could gorge themselves on hydrogen because the gas wasn't opaque and so it wouldn't be blown away. Stellar metallicity also has significant effects on the star's lifetime: luminosity, radius, mass loss, and temperature. While the effects on radius and temperature are inconsistent enough for us to ignore and may be covered later, the effects on the star's lifetime and luminosity are proportional to the power of 1/6 and negative 1/6 respectively, the metal mass fraction to the power of that. While I can't really give a consistent formula on mass loss, I can provide this graph, which illustrates that high enough metallicities, a star of any mass will blow a significant portion of its mass off, making sure that only neutron stars can form at that extremely high metallicity. But this is only at extremely high metallicities, but at extremely low metallicities, strange things can happen, like stars exploding with no remnants. So, finally, we established the final metallicity. Using the formula for stellar metallicity in the solar neighborhood, the metallicity at present is 0.5 times ln of 13.75 minus 0.75 over 12, which is 0.04 dex. In episode 1, we established the system location as very close to the galactic center, and on the border between the thin and thick disk, displaced the metallicity at about 0 dex for new stars, making the region about negative 0.5 dex lower in metallicity than the solar neighborhood. Taking this into account, we get a metallicity of negative 0.30 dex for a system being 6 billion years old, which is needed for the system to stabilize, to be fit for life, which translates to an iron abundance half of that of the sun's. So these are the final count. They're based on solar system abundances. I'll put the spreadsheet at the bottom so you can do your own. But anyway, bye. Thank you for watching, and see you later.